Let's now say that we want to solve a more general problem. So we want to compute dH1n with respect to dW1mn. So what does it mean? We pick out the mh in this layer, and we're asking for the weight that connects xm, let's say this guy, and hn, so this guy, what's the derivative? Those guys, they have to match. Otherwise, the derivative will just be 0. Because, for example, if you change this weight, well, it's not going to affect this unit at all. So the derivative would just be 0. That's not interesting. So what we are trying to compute is this guy. We're going to use exactly the same strategy. So we're going to say, well, that's the derivative with respect to W1mn of sigma of this sum. Of the sum from over, let's say, J of W1 going from J and going to the hidden unit N of xj plus B1n. Okay, so what is that? Well, we know the drill. So the derivative of the author function is just going to be h1n times 1 minus h1n. What's the derivative of this guy with respect to w1mn? Well, let's write it out again. That's going to be d by dw1mn of this sum. So that's going to be w11n times x1 plus w12n times x2 plus and so on until you reach w1mn xn plus and so on. And here you'll also have B1n. So that's going to be this entire expression. So again, the derivative of most of the terms here with respect to W1mn is just going to be 0. So you change W1mn, this guy stays the same, which means that the derivative is 0. The only exception is this guy, where the derivative is going to be just xn. So that means that in general, So in general, what you'll get is h1n, 1 minus h1n, times xm. So that's going to be the derivative of h1n with respect to w1mn, with respect to the weight that connects the mth x to the nth h1.